Okay, we're now on the second module for our nuclear chemistry topic, which is balancing nuclear reaction. This will be a very short video. It's just going to introduce to you how to balance nuclear reactions and introduce also, of course, the different types of nuclear reactions. Unlike your redox reactions, wherein you had to balance and then there was actually a process. In this case, it's very straightforward. All you have to um, remember will be five simple steps. What I did was outline them into five simple steps. Actually, you really don't have to follow all five steps, but at least you have a guide on how to do it when you come across some exercises on balancing nuclear reactions. So in the process called radioactive decay, which we just had in the last video, the nucleus breaks down by emitting radiation. The process is represented by a nuclear reaction in which, of course, the mass number and the atomic number may change. The sum of the mass numbers and the sum of the atomic numbers are equal to the reactants and the products. Okay, so in this given example, what you see here would be a mass number of 251. So let's check. We all know from the previous video that we're following the AZ format, wherein A is your mass number and Z is the atomic number. So we also know that this will be the reactant side and this will be your product side. So all you have to do is make both the atomic number and the mass number equal for both sides. So this is the product side. So let's check for California. Okay, that's 251.98. So let's see if it balances out. So here you go. So 247 plus that's 251, 96 plus 2, that's 98, and you're using what? That's 4 2HE. This is now your alpha, particular alpha emission. Okay, there you go. So this is just introducing it. That's outlining it the shortest way possible. All you have to do is again make the mass number and the atomic numbers equal for both sides of the nuclear reaction equation. Okay, and if you just want it on a more organized way on how to present it, first step, of course, is to write the incomplete nuclear reaction or nuclear equation. The second step is to determine the missing mass number. And then step number 3 will be to determine the missing atomic number. And then, of course, determine the symbol of the new nucleus, or you go to your periodic table and check which has that specific atomic number. And that will be the one with the new nucleus, if we might say. And finally, complete the nuclear equation. Quite simple. For example, for this reaction, we have 241. I guess this is americium. Let's go to our periodic table. Let's just check. There you go. Yeah, it's americium. As I've said, I think in the last video, what's constant will be the, oops, sorry for that, will be the atomic number. This one, the mass number may be different, as the case may be. Maybe when it reacts with another element, or different periodic tables would present it differently. So in our case, we'll be sticking to what's constant, and the constant number we have would be the atomic number. Let's go back to the module. So what would be the element here in this question mark? Or what would be the new nucleus? So quite simple. So first we go to for the steps, okay? And we just copy that here. That's 241.95 americium. Oops, sorry. Yields what we're looking for, and since it's um, an alpha emission, so 42. So that will be the first step, writing the incomplete nuclear equation. Next will be find the missing mass number. So we know that the upper portion, or the upper number, is the mass number. So that's 241.95. minus 4, that will be 237, I guess. And what do? We check it later on the periodic table. Since 237 is not our checkpoint, we can't just find a 237 mass number in the periodic table. Because I said, and what I wanted you to remember was the atomic number is the constant and it's the identifiable number in the periodic table. So that belongs to step number 3. So we have 95 minus 2. I guess that's 93. Not I guess, that is 93. So we got our periodic table, look for 93. So there you go. 93 is Neptunium. Okay, so we just have to write here, and our answer would be, okay, we found out that it's Neptunium 90, sorry, oops, oopsie doopsie. Okay, that will be Neptunium 93, and then we're keeping our 237. So eventually, our complete nuclear reaction will be 241, 95, aberration yields Neptunium 237, 93 plus our helium 42. And if we check this 237, if I may do this, it's 237, that's 241, this is 95, and it checks, okay? This checks. Hope that's clear. That's for our alpha emission. Now we do the same thing with our beta decay. So here we can see a beta particle. That's beta or beta. So this is 4219 potassium. So let's not follow the steps anymore. We know the steps already. So let's do it the easiest way that we can. So mass number first. So that will be 42 minus 0. That's 42. No change. For the atomic number, we have 19 minus, but that's a negative 1. Because that's negative 1 there. It's just doing really math. It's like arithmetic. So this is actually 19 plus 1. This is 20. So we're looking for the 20th atomic number in the periodic table. We go back to our periodic table. We look for 20. So 20 here. So you can see 20 is calcium. Okay, so we go back to our solution. So it'll become 42, 19 potassium yields calcium 42, 20 plus our beta emission. Okay, so this will be our answer. So let's just highlight that so that stress that this is our answer. Okay, this beta decay. And then, for example, we're doing a positron emission. Well, positron is actually the inverse of our beta decay. No changes in the mass number, but it's a positive one on the atomic numbers. So a proton is converted to a neutron and a positron. The mass number of the new nucleus is the same, but the atomic number decreases by 1. So there you go. Okay, so this will be the final equation. For example, for manganese, okay, that's 4925. No changes in the mass number. And then this will be, okay, let's check if this is 24. Yes, 24 is chromium, so that's correct. So chromium 4924 plus your positron. And lastly, for gamma radiation or gamma radiation, in gamma radiation, energy is emitted from an unstable nucleus indicated by M following the mass number. The mass number and the atomic number of the new nucleus are the same. So in this case, no changes. So it's just basically, hmm, uh, if actually when I was asked before what is a gamma ray, what is it? What does it do? If you can remember the definition, it's a burst of energy. It hastens the nuclear reaction. Though it's not giving any change when it comes to atomic number or mass number, it hastens. It's a catalyst in the nuclear reaction. Let's do zero gamma radiation. Okay, some more examples. Let's try to solve them. Let's first have this one. Alpha emission of polonium 21084. So let's answer that. That's polonium 21084. Let's not make the long solution. So plus 4 to He. So we're looking for